everybody, this is Mrs. Ewald signing in, and we are going to start Unit 3 with gases. But before we actually get into the meat and potatoes of gases, we first need to review a little bit and go through just some prior knowledge. I'll also be able to talk about the kinetic molecular theory, which helps us to understand a lot of things, and that you could find in those sections in your text. We also want to talk about the characteristics of gases and how they behave, and then also get to pressure. We'll do some calculating at the end. So, moving on. Here's a quick review. Solid, liquid, and gas. We looked at this before when we did phase changes and when we did those calculations. But let's just remind ourselves. If you have a solid, what that means is that you have those particles very, very closely packed together and forms a nice matrix, which, if I increase my temperature and I heat this up a little bit, well, eventually those particles are going to want to move further away from each other. And that is when I'm going to form into a liquid. And so those particles, those molecules now have a little bit more kinetic energy. We can measure that by their temperature. So they're going to become more and more excited. And then eventually, as we increase and spike up the kinetic energy even more and increase the amount of heat energy, they're going to be rapidly moving away from each other, and now we have a gas. So how do you make a phase change occur? We do that by increasing our energy. And now we could also use the word kinetic energy. How do you measure heat energy? We do that by measuring the temperature. And temperature is the average kinetic energy of the particles, so it's a way for us to measure it. And we looked at temperature in the previous unit as well. So when do particles stop moving? This is what gets us into absolute zero. So we always want to use absolute temperature or Kelvin when working with gases because this helps us to understand the movement of molecules. So if you look at degrees Fahrenheit, it ranges from -459 all the way to 212. Degrees Celsius, which is what we use a lot of the time, it ranges from -273 to 100. And that works out really nicely for us, just like we did in our phase changes and when we did the heating cooling curves. Kelvin ranges from 0 to all the way to 373. And one really, really nice thing about using Kelvin is that when you have something that is at absolute zero, what it means is that motion of those electrons stops. And so absolute zero is when you would have no motion of the electron. This here, and it kind of gets cut off on the bottom. So Kelvin is going to equal to degrees Celsius plus 273. So this is a way for us to go back and forth between degrees Celsius and Kelvin. In heating and cooling curves, we use degrees Celsius only because we're only really interested in the change in temperature. But when we get into gases, it's going to be very specific, and we need to make sure that we know how to convert to Kelvin and use only Kelvin in those calculations. So the what and the why, you should always ask yourself what and why. So the kinetic molecular theory, let's break it down. So we should look at what this word means. Kinetic is going to mean movement, motion, right? And theory, that is a way to help explain how something happens. So when you look at the kinetic molecular theory, it's a way for us to think about, first of all matter consists of particles, and they're going to be moving in constant motion. And then we get into the specific parts of the kinetic molecular theory. So these are the 5 main points of the kinetic molecular theory, and you need to make sure that you know them and understand them, because you should conceptually understand what your calculations mean. So first thing, each particle in an ideal gas, we are going to assume these 5 things. One of them is they're like a tiny sphere. So we're going to assume they move and they are themselves a tiny sphere that has virtually no volume. So they don't take up a lot of space. Also, they are in constant random motion, colliding and causing pressure. So they are constantly moving. They're going to be going and having elastic collisions, bouncing off of each other, moving randomly around the room. They don't attract or repel each particle, like, or each other's particles. And that's a really big thing we want to assume, because then that would affect other things. So we just want to assume that they are not, attracting or repelling in any way. And then lastly, they're going to move at a speed directly proportional to their temperature in Kelvin. And so remember, at 0 degree Kelvin, you have no motion. If you increase the temperature, you increase your amount of Kelvin, your degree, or your Kelvin temperature, you're going to be increasing that motion. And so these could all be found in page 430 in your book. All right, so kinetic molecular theory with ideal gases. We are going to assume for an ideal gas that it's going to follow the kinetic molecular theory. And when we say the gases are behaving ideally, we are assuming that they are following those 5 points that I just had in the previous slide. But understand, no gases are going to be completely ideal. But we're going to assume that they are in order for our calculations to be correct, because we're theoretically assuming that. So please understand that, especially when we get into the ideal gas law, we are assuming that the gases are ideal. Okay, so gases are going to expand to fill any container. That is one big characteristic of a gas. And that also helps us understand how we can pressurize a gas. One really good example of that, if you think about like a balloon, right? What is the reason why a balloon maintains its nice spherical shape? It's because all of the little air molecules inside are moving around in random motion, bouncing all over the place. And what are they doing is they keep hitting against the side of that balloon, which helps to maintain its shape. And it does so very well, so much in fact that it constantly appears to our eyes as a round balloon because of those molecules constantly hitting against the edge of that balloon. We don't see any dimples or anything like that. And so they are going to continually to move. Why? Because of the random motion and having no attraction. So here, if you were to zoom in on what is occurring in this picture, you would be able to see that motion. And so gases have very low densities. Why? Because we're assuming that the particles have very little to no volume. And so, again, we could see that looking at our phase change here. Gases can be compressed. Why? Because we're going to, again, assume particles have no volume, so there's lots of empty space. And so this is how we could take something, change the volume, and really increase the pressure. So here you're able to see pretty low pressure. Here now, we've definitely increased the pressure inside that container. Now, talking about pressure, we could actually quantify this and use this equation, and that is that pressure is equal to force over area. So, for example, which shoes create the most pressure? Well, any females out there know exactly what this can do to your feet. But let's talk about specifically the pressure related with it. And so pressure is going to equal the force over area. And so by having very little area, so we're going to say, I don't know. So if you look at, for example, a force of about 3, and we'll say Newton, and we have a small area of only about 1, what will happen to your pressure? Well, your pressure is going to be pretty large. Versus if I increase my surface area. So if I just take the same thing and now look at it in reverse, and if I have smaller pressure and a greater area, my pressure has now dropped. And then if I were to increase my surface area even more, so let me change this now to 1/6, my pressure becomes even less. So hopefully that helps you to see the relationship between pressure, force, and area. You should know this equation. You should be able to be comfortable what it conceptually means. All right, sorry, went too fast. All right, now as far as pressure you should know is all around us. Atmospheric pressure. So this is air particles that are going to collide with objects. So how is the pressure different in the mountains of Colorado than here in Illinois? Well, as you move up, you are going to decrease your atmospheric pressure. And so here you could see, if you were to look sorry, the picture got cut off here. But pressure in Baltimore is about 760 millimeters of mercury, versus if you are on the highest point, it would be 714 millimeters of mercury. So your pressure decreases. Why? Because your amount of air molecules are going to be decreasing. So what does this mean? Well, this is also going to affect, eventually we'll talk about how it affects boiling point and melting point based on your elevation. But we're going to look at pressure here as far as, you know, understanding this, the less of your gas particles, the smaller your pressure will be. So a barometer is a way for us to measure that atmospheric pressure. And the barometer was actually first designed and made by Torricelli in the early 1600s. Really quick story why, in case you want to know, because this is somewhat interesting, I think, is that he was always wondering, they used to have water pumps in order to get their water, and the water would only raise about 34 feet from the level of the earth anytime that it would be released. And he thought about that, you know, and he said, well, I guess it makes sense, right? So you have the pressure of the water moving up against the atmosphere, and then the atmosphere must also be putting pressure on the water. And so what he did is he used mercury. And so in the first barometer, which is why we have this unit of millimeters of mercury, he used mercury, which is 14 times denser than water. And when he did the same thing, he found that the mercury would only go up 30 inches. So it would go up 30 inches above the level of the earth, which, if you were to calculate this and convert it, is 760 millimeters. And so this is how we get the unit for pressure, which is millimeters of mercury, because it's measuring the distance of the mercury inside the barometer. And so oftentimes people refer to millimeters of mercury as torr in honor of Torricelli and his discovery. So here you're able to see a few pictures showing a barometer. It's filled with mercury inside, and then you have the atmospheric pressure also pushing down, which is then going to change the level of the mercury inside the barometer, inside that vacuum. And so here, if you have less atmospheric pressure, then you're able to see that that would also change the level inside your barometer. Manometers are what we're going to use for our calculations, assuming we only have the one open-ended. And so this measures the pressure of a gas in a container. And then here you're able to see a picture from Miss Heaton's work. I'm sure she could tell you a lot about that in class. But inside is mercury, which can be really, really dangerous. You have to be really, really careful, especially since it can shoot out and up, and we don't want that to happen. And then over here you're able to see a manometer. Again, you could see it's one open end to the atmosphere, and then the other end is going to be by that closed gas. So how do you read this? So inside we're going to assume that we would have mercury in here. And so it's an open-ended, so this is open to the atmosphere, and this end is open to our contained gas. So what happens is the pressure is going to be exerted onto that mercury and pushed down on it if it has a greater pressure, moving all of this mercury up and over, and then exerting pressure towards that gas. So here you're able to see on the right side a greater atmospheric pressure pushing on that mercury than the gas has. So the gas must have a lower pressure than the atmosphere because the mercury is able to move closer to that ended arm of the closed gas. I like to think of this as Big Bird and Elmo. And so here, if you were to have Big Bird and Elmo on a waterbed, so if this is our barometer here, like our waterbed, our levels of water, which were initially the same, if you have Big Bird sit down on that waterbed, it's going to have a greater pressure, and it's going to kick Elmo up. And so you're able to see that change here. And so from here to here, you're able to see the change. Here to here, you're able to see the change on that manometer reading. So pressure in the flask is going to equal the atmospheric pressure on the left. And on the right, it's 4 units less than the atmospheric pressure because of the fact that Big Bird is sitting down on that bed. So if you want to know more about reading a manometer, please refer to page 405 in your book. Again, if you were to look at this one, the atmospheric pressure is greater, so it pushes down on that level of mercury, causing it to rise on the other end. And how much so? We can measure this in millimeter. And so here, between the distance from here to here, we're able to then measure the amount in millimeter. Let me take you through an example of that so you can see what I mean. So if you have an open-ended manometer, first of all, anytime you do these types of problems, it's always helpful to draw a picture. And so here I'm going to show an open-ended manometer. I have my confined gas inside this bulb over here on the left, and I'm also going to want to show my levels of mercury. So the height of the mercury level in the arm connected to the gas is 26 millimeters higher. So I'm going to show my level of mercury over here higher than my level on the open-ended arm. How much difference? Well, it says that the distance is 26 millimeters. So the distance between here and here is 26 millimeters. I'm going to also draw in my mercury, just because it's fun. And so it would look a little bit like this. And then I have atmospheric pressure being exerted on the open end and pushing down on it. And we said that it's 778 millimeters of mercury. So we want to know what is the pressure of the confined gas. So we want to know what is the pressure of this inside that bulb. So to do this, it's pretty easy. The drawing here helps me to conceptually think about it. So if this is pushing down, this is like my big bird pushing down on my level of mercury. It is then pushing this up on the other end. The only way that this is able to do that is that this has to be less than the atmospheric pressure. And so, how much less? Well, 26 millimeters less. So I'm going to show it like this. 778, oop, too many sevens there. 778 millimeters of mercury is the atmospheric pressure. And then I'm going to add the difference, which is 26 millimeters. And so my pressure for my confined gas then, oops, I don't add, do I? No. Because that would mean if I were to add, that would make that 804 millimeters of mercury, which means that my confined gas would be greater, but it's not. Because I have my drawing, I'm able to see that I'm going to subtract the 26 because the pressure of my confined gas is 752 millimeters of mercury. And it makes sense because it's less than the atmospheric pressure. Hopefully you all see that. So if I were to, and let me show you this then, over here, just a little side note, I would then add 26 if my levels looked like this. If the difference here between my confined gas and such, if this was 26 here, I would then add the 26 because then my confined gas would be 804. It would be greater. That would be my big bird pushing down on my mercury, and my atmospheric pressure would be Elmo. I hope all of my analogies make sense here. Okay. So finishing up a little bit. Went too far. Some other key units that you need to know. You need to be able to convert back and forth, especially after you do barometer problems and so forth. Understand that 1 atmosphere, which is a pressure unit that we use, ATM, is equal to 101.325 kilopascals, which is also equal to 760 millimeters of mercury, which is also equal to 760 torr. Again, we use that because of Torricelli, so feel free if you want to honor him or not by using torr rather than millimeters of mercury. But both of those values are the same. You need to be comfortable going back and forth using all different pressure units. All right, and then lastly, STP, standard temperature and pressure. No, it's not the band, although that was my generation anyway. So standard temperature and pressure. If we ever say that something is at standard temperature and pressure, we are assuming that the temperature is 0 degrees Celsius or 273 Kelvin. More than likely, we are going to be using this in our gas calculations, and that the pressure is 1 atmosphere. And so if you have a gas that is at STP, standard temperature and pressure, it is this temperature and this pressure. So you always would assume that. So by the end of this, you should be able to convert temperature between Kelvin and Celsius, explain the kinetic molecular theory, what it stands for, and know the 5 major ideas, use the kinetic molecular theory to explain gas properties, as I went through, and also explain what pressure comes from. And so Be able to explain the purpose of manometers and barometers in measuring pressure. Make sure that you can complete a manometer problem. And also make sure that you can list the key units of pressure as well. And I think that just about covers everything. Um, yeah, I think we're good. So this is Mrs. Ewald signing out, and happy pressuring. I don't know, I tried.